Hello, everyone. This is Gokul Alex, and thank you so much, Sai, Manvi, and team for your time and interest in quantum computing. I'll be sharing screen right now. If you are able to see, please confirm. Okay, so I have shared my material. I hope this is viewable to everyone.
Yes, Gokul.
Okay, last session I was giving you an introduction to the quantum computing architectures. I will be able to, I've shared the material with all of you in Slack. So if you have any questions pertaining to that material, you can ask in Slack and in this community, or you can ask in future sessions as well. Right now, we are going to survey some of the historic beginnings of quantum computing, and we will look at the contemporary innovations in this space. When all of you look at the world of quantum, one name that resonates pretty often is Richard Feynman. This is the quote from Richard Feynman on the world of quantum. This is the original quote from Richard Feynman. Richard Feynman says, when you're trying to find simulation of physics, it seems to be an excellent program to follow out. So the basic area in which Richard Feynman thought about quantum computer application is simulation of nature, simulation of physics. And you have to understand this is the statement in 1985 or around the time. And he was saying the conventional computer simulation of physics, he's not far happy with the analysis as per the classical computing theory, because nature is not classical. In Richard Feynman, in his own style, is saying nature is not classical. If you want to make a simulation of nature, you would better make it quantum mechanical. And it's a wonderful problem because it doesn't look so easy. This is the very interesting statement about quantum, the quantum nature or quantum computational nature, and how quantum simulations can play a pioneering role in understanding a world very closely. That this is way before the time Peter Shor and Love Grover and David Deutsch, all of them worked on quantum algorithms. This is quite a very strong vision in Richard Feynman that we are seeing here. When you look at the nature, the quantum computer would be able to absorb natural events, natural data sets, natural movements, phenomena more closely. What are those natural phenomena? For example, photosynthesis, or the formation of nitrogen on air, on the atmosphere, or formation of magma after the volcanic eruptions, or seismic vibrations, weather changes. Wherever you look at, when you look at nature, whether it's below the thermodynamic limit or above the thermodynamic limit, nature exhibits a wide-ranging variety of events that can only be interpreted properly by quantum mechanics. It's very evident when you look at some of the phenomena like photosynthesis, which I can explain in one of the future sessions in detail. How the optical energy, how the electromagnetic energy gets converted into biochemical energy. That's a marvelous example of a quantum energy transfer. If you talk to any computational biologist, if you talk to any computational, somebody studying computational biology or bioinformatics, they will be able to explain you the wonder, the magic in photosynthesis. So, or when you look at the hybridization of molecules, hybridization of very complex molecules, you must have studied about them, like hybridization of iodine fluoride, or hybridization of, you must have heard about hybridization like sp3d3, sp3, spdf. You remember all those orbitals, right? So any molecular architecture or the polarization or spin of an atom or spin of a nucleus, movement of electrons inside an atom, or formation of ions. In all this phenomena, these phenomena, it's very difficult to interpret in classical terms. Now, what is David Deutsch, another preeminent scientist from, he's from United Kingdom. He was it seems he was a professor in Oxford or Cambridge. What is David Deutsch talking about quantum computing? Computing machines resembling a universal quantum computer could, in principle, be built and would have many remarkable properties, not reproducible by any Turing machine. Complexity theory of such machines deserves further investigation. This is a very very prophetic statement. David Deutsch is the person who invented quantum Turing machines in the future. I mean, after the statement, he categorically explains that classical Turing machine design won't be sufficient for a quantum Turing machine. In one of our future sessions, we will see the details of quantum Turing machine. So this is the statement. You must have, I'm not sure how many of you have studied about Turing machines in your schools. Turing machine is a thought engine, I would like to say Turing machine is a model of computation, one of the first model of a computer. Like there are a lot of others who worked on, like Alonzo Church or Konrad Zuse. Alan Turing was one of the pioneers who worked on the essential attributes and properties of a computer. When Alonzo Church came up with lambda calculus, Alan Turing came up with his concept about visualization of a computing device. If you go and search about, read his papers online, that would be a marvelous read. You can read his papers and his passion for science and technology. Okay, so now we should go and look at the history of quantum computing. It's very interesting to see that the early seeds of quantum computing began in 1950s itself. From 1950s to 1990s, primarily there were theoretical research with limited physical experimentation, because there was no consensus among researchers and academicians on quantum computers. And from 1990s onwards, there are plenty of research on quantum computers, like IBM and universities in Germany, US, Australia, Canada, and Britain. They have done tremendous research. We should be proud to know that our IISc Bangalore has done one of the first prototype of quantum computer in 2005, around 2005. They have created a quantum computer using nuclear magnetic resonance based quantum computer. So if you ask us, in India was one of the front runners, even though right now we are not one of the leaders. If you ask now the leaders, you all of you know the leaders in the space: US, Australia, UK, Canada, Singapore, China, and Japan. These are the global leaders in quantum computers. But we have the talent, we have the talent to match with any of them. And when you look at the evolution, so from 2010 onwards, there has been, there are a lot of, can you please give me a moment? I'm getting a call.
Karthik is
Sure,
not
sure.
complete.
Guys, till now, any questions? I think now it is only introduction
Okay, guys.
to quantum. I
Thank
think
you,
in the continuous consecutive sessions will be on definitely going into the physics part of it. And also, as you guys are already learning the Q sharp parallelly, so I think it will be a great blend of both the theory as well as the practical. But if you guys have any questions, feel free to reach us over the Slack.
Great, great. Yeah, I will get into the physics part of it, physics and mathematics part of it in the subsequent event sessions. Okay, I know that there is exams coming in, so please don't worry if you don't have time to research now. I'll give you a very good in-depth analysis on the physics part of it in the coming sessions. So let's move a bit faster. And okay, so right now, as we have seen, quantum computing has taken a good pace, acquired good pace ever since 2015 onwards. Let me take you to the initial days in quantum computers. So in 1960, Stephen Weisner invented conjugate coding. This is a very interesting project. On the right side of this, you are seeing an apparatus of a quantum computer here. Okay, so conjugate coding was the first concept which later became the foundation for quantum teleportation, the exotic idea which has not yet materialized in its full dimension. 1960, that is, you can understand how early it was. In 1973, Alexander Holivio publishes a paper, that remarkable paper that says quantum bits can carry more information than classical bits. And but at the same time, classical bits are more accessible. This is known as Holivio's theorem or Holivio's bound. And then we can see the research is gaining momentum. In 1975, R.P. Poplavsky publishes thermodynamic models of information processing, in which he shows the infeasibility of simulating quantum systems on classical computer. This is a very landmark research that proves that quantum mechanical events and phenomena cannot be simulated with full accuracy on classical machines. If you know, there is a software known as Schrodinger. Schrodinger is a software in which you can simulate the movement of atoms and molecules, but it's just a simulation. It's not a true representation. And in 1976, Polish mathematical physicist Roman Stanislav publishes a paper called Quantum Information Theory. This may sound a bit difficult for you because you have not studied information theory yet. Information theory is something which you study in your initial years in computer science. Okay, but you can say that these were the groundworks. And in 1980, a physicist known as Yuri Man proposes the quantum model. In the same year, another physicist, Paul Benioff, suggests quantum mechanics could be used for computation. And by 1981, Richard Feynman in Caltech coins the term quantum computer in front of a esteemed audience. And that's how he could popularize the concept of quantum compute. That was a defining moment for quantum computers. This 1981, Richard Feynman, in front of a lot of the experts, quantum physics experts, he presented the concept along with another physicist. In 1981, Tommaso Toffoli he introduces one of the first quantum gate. It's a Toffoli gate. It's known as reversible Toffoli gate. You will understand more about the theory of quantum computer, like in future sessions. Like you can refer to my material shared in the Slack. There I'm talking about the fundamental quantum gates. So for almost all the classical gates, there is a quantum counterpart. Like there is a NAND gate. For NAND gate, there is equivalent CNOT gate. There is a root of NOT gate, Toffoli gate, swap gates. We will study about all those gates in the coming sessions. And in 1985, not so very suddenly, very quickly, David Deutsch, he's another very famous, we heard about him in this session. David Deutsch develops a quantum Turing machine, showing the world that quantum circuits could be universal. So they could be used for universal computation. And then 1985 to, there are a lot of things happening in between 85 to 1994. But the landmark event is in 1994, mathematician Peter Shor invents the algorithm. And in 1997 itself, an Indian, Love Grover, develops a quantum search algorithm with O, root, and complexity. You will study about the big O notation. This is known as big O notation, which is used in computational complexity theory, which I will be covering in future sessions. And then there is a plethora of research happening. I have not covered all of them. A lot of research is happening between 1997 and 2007. But 2007 marks a landmark event when D-Wave, a Canadian startup, announces a quantum computing chip that claims to solve Sudoku puzzles, triggering years of debate. So this is, you can say that this is a quantum optimization. D-Wave was focusing on quantum optimization problems using the computer we mentioned last time. They use annealing, quantum annealing. It's a adiabatic process which you are studying in physics right now, right? So it's an adiabatic model of computation. And then actually this person, the founder of D-Wave, was an IBMer, and he came out of IBM and started this company. And I guess that's right. And then 2013, Google teams up with NASA to fund a lab to try out D-Wave hardware. So you can say that Google and NASA were one of the early promoters of quantum computing research in the public domain. And then 2014, Google hired the Professor Martinez. He is currently with Australia, but he was instrumental in building some of the landmark quantum computers milestones in Google. And then there is a competition between Google and IBM. IBM puts their prototype in 2016 on the internet. That is what you are accessing now as IBM quantum experience machines. So that they launched it in 2016. And I was very fortunate to have accessed that machine even a little while before, because I was working for IBM those days. And in 2017, Rigetti, another startup, it's founded by Chad Rigetti. They open sources their own quantum computer to build prototype. So we can say Rigetti is one of the first, Rigetti and D-Wave are one of the first startups to work on quantum computing space. And then you see a lot of industry, heavy weights in the industrial sector getting into quantum business. Damier and Volkswagen, they started working on quantum computing. And then, is there a question? Okay. So we have, I'll quickly wind up today's session. So Microsoft also started working on quantum computer along the same lines. And then this is the diagram of Google's Bristol quantum computer, one of the leading quantum computer from Google, Bristol and the other one is Sycamore. These are the latest announcements from Google. Google is currently working on their own quantum machine learning experiments and quantum hardware experiments. But Sycamore and Bristol are two milestones in the world of quantum computing. This is the diagram of the quantum annealing model created by D-Wave. This is the visual diagram. And then IBM's quantum computer, this is 53-qubit IBM quantum computer photo. And Intel has also come up with the 49-qubit quantum computer. They launched it in CES 2018. It's codenamed Tangle Lake, 3-inch by 3-inch chip. And Intel worked with the partner QTech in the Netherlands. And they also came up with the quantum computer measurement system. It's called, this is the tool. This helps you to test a quantum computer. It's called Cryogen Wafer Prober. Looks pretty exotic, right? This is the machine which Intel has invented to measure or test the quantum computer. And this is the photo of Rigetti's quantum computer infrastructure. And this shows IBM Qiskit. Qiskit is an infrastructure, software platform from IBM. This shows some sample code. How do you initialize quantum register, classical register, quantum circuits, and how do you, so you can see that how to measure the output from quantum computer from this. I'll go through the code in detail in the coming sessions after covering the physics part, if that is okay with you. Qiskit Aqua is the quantum compute, one of the, so earlier I mentioned about QS Aqua, QS Terra, and QS Ignis. QS Aqua contains quantum algorithms for quantum chemistry, quantum optimization, finance and AI use cases. And this is another company, Xanadu. Xanadu is completely focusing on quantum machine learning experiments. They have, this is Xanadu Strawberry Field. And then photonic quantum computer is another area, a very exotic area, which may give better fidelity and better, it will have lesser decoherence errors, noise, compared to the superconducting quantum computers. That's why there are a lot of interest on photonic quantum computers. Okay, how quantum computers work? This is the inside look on a quantum computer. I guess time will not be sufficient for me to cover this. So we can continue in the next coming sessions. And so kindly share your questions and your doubts, feedbacks, and suggestions, if any, in Slack. We will continue the conversation. If there are any questions now, I think we don't have much time left. So can we finish today's session, Sai?
Yeah, yes, Gokul. Just one closing words from my side. I think, guys, as I told you earlier, I think these are the introductory sessions which will be having the base for the future discussions, I would request you guys to go through this deck. I mean, I will also make sure that the deck is available over the Slack, right? So if you have any questions, make sure that the Slack channel is active, and we will be, myself, Gokul, will be watching out there. If you guys have any questions, feel free to reach out to us in any, I mean, in any sense. Not only, I mean, if you have any questions with respect to computer science, I think we are free to take it, but please put your focus on quantum computing right now, right?
Great. Yeah.
And also I would request all the students to share the summary